Now that we have a good understanding of the basic operation of a MOSFET, we're ready to talk about our current voltage characteristics, or our IV characteristics. So the first mode that we can talk about is if our gate to source voltage is lower than our threshold voltage. So if we have VGS less than VTN, then our device is essentially turned off. We don't have an inversion layer, so we have no current in the MOSFET, and we say that we're operating in the cutoff region. Now, as we talked about realistically, our threshold voltage corresponds to strong inversion. There is going to be some current even if we're right below our threshold voltage, but we'll come back to that when we talk about non-ideal effects later. So let's say we now increase this voltage above our threshold voltage. So sort of our second more interesting case is now we're going to say our VGS is greater than that threshold voltage, VTN, so we can have small values of VDS, voltage between our drain and source, which is going to produce some current. So small values of drain to source voltage, VDS, is going to produce currents through that inversion region, which is created by that gate voltage above our threshold voltage. And so these, for small values of VDS, we're going to see linear increases in our drain current as we increase that VDS value. So it produces currents that increase linearly with our changes in our VDS. And so let's take a look at that graphically. So let's say we have our ID over here, and we're plotting that versus our VDS. So we have VDS and ID. And so what we're saying is if we have some gate voltage, let's say we have some gate voltage VGS1, and so I keep saying gate voltage so it's inherently referred to the source, but let's say we have some VGS1, which is greater than our threshold voltage, VTN, and what we're going to have for small values of VDS is some linear curve that looks like this. Now, what if we increase that gate voltage a little further? So what if we say VGS2, which is greater than VGS1, so of course it's inherently greater than our threshold voltage, then we're going to have a steeper slope, so we're going to have more current for a given VDS. So we'd see something like this. Now, keep in mind, this is for small values of VDS. So what happens if we continue to increase that VDS value? So let's think about the physical structure of the device. So let's say we're going to continue increasing our VDS. And so as we're increasing that VDS, let's think about what's going on physically in our device. So I've got sort of a rough structure shown here. We're sort of looking at our MOS capacitor almost here in the middle. And we just said, yeah, we have some N-type region with our drain where we're connected externally and some N-type region for our source. But let's just focus on the middle right now. And so of course we know if we have this VGS1, which we said above is greater than our threshold voltage, we're going to have some inversion layer. And so we can represent that as maybe a highlighted region, something that looks like this. And so that's going to be our inversion layer of electrons, and so that should just be in the semiconductor, not going into the oxide. And so that's going to provide some path for our electrons to flow between our drain and source. And so what we can see is if we continue to make small adjustments, as we said above, we're going to see this linear increase. So this is sort of the case we already considered above. So we're going to see some linear increase for small values of our VDS. However, as that VDS continues to get bigger, it's going to start counteracting our VGS. So let's go ahead and write that, and then we'll come back to our model. So as our drain source voltage increases, it's going to start counteracting our VGS, or another way that we can think about it is it's reducing our effective VGS at the drain. So reducing our effective gate voltage at the drain. So again, let's take a look at sort of what's going on in our model here. So let me be a little more careful about drawing our inversion region this time. So what we're going to have is maybe we can think about our gate voltage at any point between our metal and our p-type region. And so what we would see is, of course, over here on this side, we're at a ground potential. So we're going to have the full VGS value. However, as this VDS gets larger, we're going to have some positive charge here, or some positive voltage rather. So we're going to have to work a little bit harder because the relative voltage from, for instance, this point over here on our gate and this point on our drain isn't going to be the full VGS, but rather it's going to be VGS minus our VDS. So we have to sort of overcome any voltage that's applied to that drain. And so again, the net effect is that that VDS value is going to be reducing our effective gate voltage at the drain. So now if we have an inversion width over here that's something like this, it's going to be decreasing to something like this as we move over towards our drain. So what we see is that we're sort of getting narrower as we increase that VDS value. And so if we think about sort of a pure resistor, or a pure conductor that's acting as a resistor, as that diameter or that area that current flows through gets smaller, for the same amount of voltage, we're going to have less current. So what we're going to see in terms of our curve then is we had this linear region we talked about before, but as we keep increasing, we're going to start seeing a bit of roll off now. So we no longer have that linear relationship. So no longer linear. So we start sort of dropping off a little below what we would expect if it was continuing to be linear. Okay, so of course we can sort of keep on pushing this a little bit further, and let's say we keep on increasing this, and eventually we're going to get to some point called the saturation point. So what we can say is if we keep increasing that, and I think eventually, let's go ahead and look at what this is going to look like on our plot. So let's say again we have this sort of same width over here, and so let me switch to green. So we have this same width over here, but now we've increased this until we have, it comes right to this point here, right below our oxide at the drain side. So this particular point is going to correspond to the transition between our non-saturation and our saturation region. So this is going to correspond to a certain value of VDS, which is equal to VDS sat. So VDS equals VDS sat is going to be the gate voltage. So this is a certain value of VDS when the gate voltage at the drain is equal to the threshold voltage. So gate voltage at our drain is exactly equal to our threshold voltage VTN. And so what we say is that this is, we have pinch off of our channel. Okay, and so an important equation then is we can say the VDS sat for a given device is going to be equal to whatever our gate to source voltage is minus the threshold voltage for the device. So that's going to be an important equation that we use a fair amount. And so that just comes from the fact that we know sort of what I've written up here in words is that at this point we know that VGS minus the VDS sat is exactly equal to our threshold voltage VTN. So rearranging that, we can determine a value for our VDS sat for a given operating point and a given device with a VTN. So again, what happens at this point is coming back to our curve for our ID versus VDS, we've already said we had sort of this linear region, and we said we then had this sort of roll off going on. And so at this point we've sort of we've not maximized, but we've reached a point where we're no longer going to be increasing at all. So this point is going to correspond to, of course, our VDS sat down here, and we're going to have some saturation drain current as well, ID sat. So this is VDS sat. Okay, so we can actually, and so this would be, again, the maximum ID, but it's going to be saturated at that level. So we can continue increasing this VDS actually, and what's going to happen is that pinch off point is going to be moving into the channel region. So let's say, come down here and we're going to continue increasing our VDS above our VDS sat. And what's going to happen is that pinch off point is going to move across the channel towards our source. So let's take a look at our structure and then our curve as well. So what's going on with our structure is now that pinch off point isn't at our drain, but rather it's somewhere here in the middle of the channel. So now our inversion layer looks something like that, our green area there. And our pinch off point is right here somewhere in the channel. And so again, this is occurring for some VDS which is greater than our VDS sat. And so of course what we can see now is if we look at the difference between our gate and our drain at this point, the difference there is actually below our threshold voltage, so we don't have enough positive voltage to create an inversion layer right here. So you might be thinking, well, we have this sort of gap region, so we shouldn't have any current again. And so that is actually not what's going on, because we're looking at a simplified diagram. So recall we have, in this case, a P-type substrate, so that means we have an N-type region here for our drain. And because we have a positive voltage being applied to that N-type region, we're going to have a reverse biased PN junction. So reverse biased PN junction between our drain and our substrate. And so remember, with our reverse biased PN junction, that's going to create some depletion region. It's going to be larger in reverse bias, and in our depletion region, we're going to have some electric field. So our electric field in this configuration with a P-type substrate, so an N-channel device, is going to be in this direction. And so what that means is, remember, electrons are coming from our source and they're moving this way towards our drain. And once they get to this point, they're swept across this region by that electric field. So we can say this electric field is sweeping electrons across that gap, we'll call it. So sweeping our electrons across that gap. So we do actually still have current, but we're no longer able to increase. So remember, we've already reached our maximum by reaching that VDS sat. So sort of putting all of that together is we had that linear region at the start. We said then it sort of begins to roll off. At some point we reach our VDS sat. And once we increase above VDS sat, we're just going to be sort of maintaining that constant ID max. So that's going to be our maximum ID. So again, we're sort of generally talking about these different modes. And so in the next video, what we're going to do is we're going to come back and we're going to look at a family of IV curves, and we're going to talk about these different operation regions. And so just real quickly, let me at least label this one. So once we get to this point and we're above VDS sat, we would say that our MOSFET is in our saturation region. And so we've talked about our cutoff and our saturation region. And so in between those two, we have our non-saturation region. And there's a couple other names that we'll go over in the next video. But again, as you can see, this is dependent on our gate to source voltage as well as our drain to source voltage.